This is section 1.5, example 1. Solve y prime plus y times tangent x equals sine 2x. This is definitely linear, homogeneous, non-homogeneous, ODE. So if you rewrite it, so it's dy plus y times tangent x dx equals sine 2x dx. Then you factor dx out, then y tangent x minus sine 2x dx plus dy is 0. Assuming that we could find the integrating factor f, we could multiply the f and we get exact ODE 2x dx plus f dy is 0. Then this should be exact if we can find such an integrating factor f. So this whole term should be m and this term to be n. So the exact condition dm over dy is dn over dx. We have to satisfy that condition. So df times y tangent x minus sine 2x, this whole thing, over dy is dn is f over dx. And this is, it's in terms of y, this first term is just f times tangent x, and the second term is there's no y terms there, so it's 0, it becomes 0 on the partial derivative of y. And that's, since f is function of x only, this is dx, right? So we can separate it by doing df over f equal tangent x dx. And we integrate both sides. And from the integration table, this is ln f, this is minus ln cosine x plus c star integral constant. So here, if you take an exponential on both sides, we get f and e to the minus ln. So I'm going to take minus to the power of here, so it's 1 over cosine x becomes. So it's a secant x there, so it'll be secant x times c. Actually, this, we're going to have this constant later on. So actually, from here, if I'm just skipping a little bit, this becomes this. And even this integral constant, if we need, and we have more integrals that coming on, so it'll be included in the final constant, arbitrary constant. So we can safely assume that f equals simply secant x. Okay, let me just, this is the integrating factor that we are looking for. So if we put this integrating factor f back into this ODE, then what we get is y times tangent x secant x minus sine 2x secant x dx plus secant x dy is 0. Okay, this is exact ODE. And so this term is m, this term is n. So dm over dy equal tangent x secant x dn over dx is, so the derivative of secant x from the integration table is tangent x times secant x. So they're the same, so it's exact ODE. So recall from that du over dx is m. So u is integral of m k of y, right? So u equal integral of m is y tangent x secant x minus sine 2x secant x, and dx plus k of y. And we have to utilize du over dy is n, so du over dy equal, let me take it back. We have to evaluate that one first, okay, before we move on. Let's simplify this term a little bit further to move on. So here sine 2x is, since sine 2x is 2 times sine x cosine x, and this is 1 over cosine x, we could reduce it to times 1 over cosine x. So we could reduce it to 2 sine x. So if we rewrite it, that's y tangent x secant x minus 2 sine x dx plus k of y. I left this term untouched because if you do the integration, that's simply secant x. So this integration will give secant x times y here, if you do the integration here, and this term is simply plus 2 cosine x and plus k of y. The next step is utilize du over dy is n. Okay, so du over dy is, the first term has y there, so it's a secant x, and there's no y term there, so there's no y, and k derivative is k prime equal n is here secant x, and from here k prime is 0, so k is c, hence u is secant x y plus 2 cosine x plus c. If you're still confused with this integral constant, you could always verify that you put tilde or star other than c here, and then that u is the implicit solution of that. So this one has to be some arbitrary constant, right? And if you move that over, so final answer will be secant x times y plus 2 cosine x is c. In this case, c is c star minus c tilde. Okay, so this form is easy to explicitly express in terms of y. So y is minus, so cosine x times c minus 2 cosine x. Okay,